Ladies and gentlemen, my name is Raras Maya, and I am a lecturer from Department of Information Systems ITS, and I will be the moderator for today's event. We are welcoming all of the participants of the fourth and last session of Adjunct Professor Program 2022. This event is held by the Department of Information Systems, Faculty of Intelligent Electrical and Informatics Technology, Institut Teknologi 10 November, ITS. The topic of this year program is about IoT-enabled service, with the specific topic of today's session is about Industry 4.0 and beyond. We would also like to welcome our honored speaker, Professor Shuo-Yan from the National Taiwan University of Science and Technology. Welcome, Professor Chou. We are very honored to have you here.
Thank you. Very happy to join you again.
Okay. The objective of the Adjunct Professor Program are to activate an international academic atmosphere in the ITS environment, activate the culture of international publications, increase the number of ITS international lecturers, and increase ITS reputation in the world. Department of Information System ITS has already held a Adjunct Professor Program since 2021 with the same topics, which is about Internet of Things, and the recordings of this and the previous Adjunct Professor Program can be seen on the YouTube channel Sistem Informasi ITS. The learning objective of this program is about IoT, in which IoT connects the digital and physical world by collecting, measuring, and analyzing data to predict and automate business process. This course gives a foundation in the IoT, including the components, tools, and analysis by teaching the concept behind the IoT and a look at a real-world solution. The learning objectives are understand the definition and significance of the IoT, discuss the architecture, operation, and business benefits of an IoT solution, explore the relation between IoT and digital transformation, and able to understand the application areas of IoT and examine the potential real-world opportunities that IoT can uncover. This year, Adjunct Professor Program is delivered in 4 sessions, in which this is the 4th and last session in this program. In the previous session, we already talked about data integrity to innovative business models. Today, we will learn about Industry 4.0 and beyond. In this session, we will also have demo that will be delivered by Professor Chou's laboratory members. And afterwards, because this is the last session of this year Adjunct Professor Program, we will also have an exam. Okay, before we start the session, here is the rules for this meeting. Please use your full name in the Zoom meeting, turn on your video, use the virtual background, and fill the presence. You can raise your hand in the Q&A session or write in chat if you have any question. And certificate of attendance are available for participants who joined all of the 4 sessions. And then another certificate will be added for participants who passed the evaluation. The evaluation of this Adjunct Professor Program consists of 2 evaluations. The first is the examination that will be held in the end of this session. And then the second is a mini project in which the description of the mini project will be delivered also in this session. The link for the presence form, syllabus, and virtual backgrounds will be sent in the Zoom chat later. This is the schedule for today's session. The first agenda is opening speech. Maybe I will, Professor Erma, would you like to give a short speech for today's session?
Yeah, thank you very much, Bu Raras. Yeah, good afternoon, Professor Chou and everyone. Yeah. Okay, today we are very happy to have Professor Chou, even though Professor Chou is very busy, but still have time, yeah, to give this lecture. So we are happy and very thankful to Professor Chou, yeah, and also Pak Indi as well as Pak Mujahidin as our department chair, and also Bu Raras Maya as the moderator, and all the team of Adjunct Professor members. Now we are coming to the last series of this session. So we said we will have the new topic for this session. We will also have an exam. This exam is designed, to see the understanding of the participants. So no need to feel uncomfortable for the exam. Just relax, just do the exams and enjoy the exam. It's only a bit evaluation from us to see your understanding. Thank you very much, Professor Chou, Pak Indi, Bu Raras, Pak Mujahidin, and all the teams. We hope that we can see all of you again for the next Adjunct Professor program with the other interesting topics. Okay, thank you, Bu Raras. And I think I will return this session to Bu Raras. Thank you very much, Bu Raras.
Thank you very much, Prof. Erma. Okay, next we will move to the next agenda, in which is the lecture by Professor Chou that will be delivered for 1 hour. And then there will also be some demo from Prof. Chou's lab member for about 15 minutes. And after that, we will have a Q&A at the end of the session. But after we close the meeting, the participant can do the examination for about half an hour. The description about the examination and the mini project will be delivered before the closing session. Okay. Before we start, let me introduce our honored speaker first. Professor Shuo-Yan is a distinguished professor and director of Center for Internet of Things Innovation in NTUST, Taiwan. His research interests are including Internet of Things innovation, industrial Internet of Things, big data analytics, artificial intelligence, smart city applications, blockchain application, intelligent transportation systems, entrepreneurship, decision theory, digital manufacturing, and computational geometry. Okay, let's not wait too long. Please, Professor Chou, could you give your lecture for about 1 hour?
Yes, let me see. Yay. So I just found that it's still somehow not being able to.
You can try now, sir. I have enabled the function.
Enable the function now? Okay, let me see. But the it was just like last time. Somehow I couldn't
share your screen.
Share my screen.
Oh, okay.
I see the I'm trying to share, but then let me see. Okay.
We already give permission for you to share your screen, sir.
Okay.
Okay.
I think now it's okay.
Yeah.
Okay.
I just realized what happened. Okay. Okay. Very happy to see all of you. Thanks, Rawa's introduction and Professor Irma's also introduction. So this is the fourth lecture that I prepared. Again, during this 4 weeks, I started by introducing some basics of IoT more on the hardware, software, platform, infrastructure. Then I talk about general application and also data analytics during the second week. Last week I was talking about data integrity, which is basically the key issue of the web environment and the data analytics environment, because we can get the data, but we are not sure whether or not we can trust the data. And a lot of data can be transmitted through a digital system, but the value cannot be recorded in the digital system. The value cannot be transmitted directly through the digital system. So basically, I introduced blockchain, and also I quickly described some application based on the integration of IoT, AI, which is mainly deep learning, and blockchain, how they can combine to provide a more sustainable application. So I mentioned about Michael Porter's framework on how internet can integrate all the physical system and create a system of systems. Then I also mentioned about a model that we created. It's called outcome economy. Well, outcome economy wasn't what we proposed. It was proposed in World Economic Forum around 2012, which is about 10 years. It's mainly to emphasize that once we have Internet of Things, then physical system can be connected and coordinated constantly. So we should be able to utilize this connectivity to form a hardware system. They will work together to provide the functions that individual provides. So altogether, we can have a system with the coordination of these physical devices providing us services. But usually the services are not the final goal. The final goal is more subtle, or is more direct to users. So rather than just using hardware system, we can also, since we are connected online already, we can also integrate other systems. So Michael Porter used this agricultural example, telling us how to form a system of a system so that we can change our focus on getting a device and trying to utilize the device to create the best result. Changing from focusing on a partial result, we can focus on the overall holistic result, that is the harvest, rather than the intermediate results. So agricultural machines is to ensure us to have a good harvest. We can profit from that. We can generate enough food for everybody. But in the past, we can only focus on our own part, and all the systems are fragmented. It's very difficult to coordinate them and allow them to improve their efficiency or effectiveness. But with Internet of Things, all these things can be connected together. Data can be analyzed. If they are not cannot be analyzed, we'll convert them from unstructured to structured, combining all these data and allowing the system to flow, allowing the data to flow, and we can trust each other in the cooperation. So we use blockchain, AI and blockchain, so that we can create a lot of innovative application. I just provided one example and indicating that by having IoT collecting physical data and also storing data on blockchain or trading with blockchain, and then also using AI for predictive maintenance to lower the cost, having this economy of scale, so that outcome economy can be a financially viable model, and it is also a sustainable model. And this way I'm moving towards, I think should be the most, I wouldn't say most, maybe not most popular, but it was definitely one of the earlier or earliest IoT development, which is in smart manufacturing. Smart manufacturing came together with Industry 4.0, or so-called 4.0 came along with Industry 4.0. Now we have medicine or healthcare 4.0, education 4.0, transportation 4.0. All of them are implying that the new system should be connected and data-driven. Connected and data-driven. That's our system nowadays. But I'm just going to focus on Industry 4.0 to illustrate that by being able to connect machine together.
Iya, coba. Aku bentar ya Mas,
this
Profesor.
is a data-driven approach. Then we can create a smart manufacturing that fulfill the needs of Industry 4.0. So going back to the issue of Industry 4.0, there were a lot of discussion. There were a lot of claims that they are working on Industry 4.0. Of course, we can imagine that there were a lot of new technology have been developed over the past 10 years or even longer. All of them make contribution to manufacturing. But in terms of Industry 4.0, in terms of smart manufacturing, we want to ask, what is the core of the new movement? What is the key technology that enable us to have smart manufacturing? Or what is the goal, the ultimate goal of Industry 4.0? One thing that I want to emphasize is what we want to enhance, improved, or even enabled is not focusing on mass production. It's on personalized or just mass customized production. So we want to have the manufacturing technologies which allow us to manufacture smaller batch, high variety products from the market, requested from the market, from the customers. And it is extremely difficult because if you understand the traditional manufacturing, they are not IT systems. They could be connected, but they are definitely not the kind of IT system we have for enterprises or e-commerce or for personal use. For manufacturing, their IT system is hardware, hardcore. Connectivity is through very low-level communication protocol. They don't want their machine being accessed wirelessly because it's not stable. They don't want to have high-level programming language because it's quite unknown in between the high-level programming and machine control code, whether or not there are some malwares or there are some glitch there that may cause the problem of the manufacturing. So they are very conservative, and then manufacturing, although are connected to, but their connectivity is definitely far from our advanced IT connectivity. They don't have flexibility. They are using all kinds of protocol. Joining one machine with other machine, joining one brand with other brands are always a problem. Their protocols, even with the same protocol, there are some variations. And for them, it's also natural. They want to move forward. They cannot wait for the consensus of common protocol before they move. They'll just go ahead and move it. And as long as they can satisfy the needs of their customer, they'll continue to move forward. And so they sort of bifurcate or branch out. So they may conform to certain protocol, but for the basic parts, they are okay. But a lot of time, you cannot really communicate very well. So these are the problem of the manufacturing. Then it's very difficult to change the process efficiently, because now we can just add another computer into the system. Everything is connected. Everything is okay. but for manufacturing, it's not the case. Okay, so that's so if you want to change your mass production process to this so-called high variety, small batch, high variety production, then it's very difficult. So, which means that we need to have new information technology, new connectivity, so that we can allow them to have this flexibility. So again, Industry 4.0, just like other initiatives using this 4.0, I personally will emphasize that we are not making mass production better. That's not our goal. We are trying to have more personalized or customized production, or in other industry, more customized services. So healthcare should be focusing on personalized healthcare. Education should be focusing on more flexible, more personalized education. If we talk about agriculture, we call it precision agriculture. It's not mass produced. We can change our configuration based on microclimate. We can have very specific process, making sure that different fish or different fishes can be brought up in very precise way, so that they are healthy, they grow faster, and so on. So this is the initiative which Germany saw in 2012, that 20 years from then, the socio-economic environment in the world, particularly on the demand side, very uncertain demand, high variety of product that they need to be able to provide. On the social side, aging society, not enough of skilled worker, and the factory are not allowed to have pollution, and so on. So basically, Germany at that time was asking themselves whether or not they will be able, with their technology at the time, which was leading the world at the time, whether or not they have the ability to cope with the socio-economic environment 20 years from them, which is 2032, let's just say. And their answer was no, they don't have that kind of capability. So Industry 4.0, I usually emphasize, this is paraphrasing what they said. They said that, in fact, in order to cope with the socio-economic environment 20 years from now, from them, this is what we envision that that the manufacturing system should be, if it can be realized. So even for Germany, they are not sure what it should be done. And the goal is clear, but how to approach the goal is not that clear. And they came out with a framework, and they continue to push it. And even at the time, they said that if we can accomplish it, I think this is what we envision that it should be. Okay, so that would be my point. And quickly, Industry 4.0 was equated to the fourth industrial revolution, which is very major. You can imagine. The first industrial revolution, we have machine, a steam engine, a machine replacing human. I think earlier there were two questions about replacing human. But again, first, second, and third industrial revolution, we all had the fear. And fortunately, the displacement of job, replacement of human worker did not put these unused human resources in jeopardy. In fact, they were better trained and do very different jobs nowadays. So first industrial revolution, second industrial revolution, I think most of you are quite familiar with, is mass production with the conveyor, allowing division of work, and also electricity, allowing us to transfer power in long distance. So we have mass production system. You can imagine with mass production system, we can produce a lot of product. But gradually there are labor problem, and not only human do not want to work that long hour, human need to rest, and human make errors and so on. So the third industrial revolution, I think nowadays we consider as automation, with electronic and software and IT introduced to manufacturing environment. Before that, we still need to have human, right, as the main control part of the manufacturing system. And manufacturing line build mass-produced product, but humans are working more like machine in between, following the movement of the system. Now with automation, a lot of physical job, right, were replaced by machine. They can be programs, like programmable logic controller, right? They are a little bit of system like manufacturing execution system, or at the enterprise level, we have ERP coordinating the manufacturing. A lot of thinking, coordination, flexibility, I have to say, were still done by human. Automation is automation. Replace human because it's repetitive. It doesn't require human. Machine can do very well. We give the machine a program, programmable logic controller, read the code and follow the process. They are different process, but machine will follow the process, resulting in automation. But automation, because machine did not have intelligence, machine follow process, but machine do not make judgment usually. So automation is, if we compare with Industry 4.0, which also has automation, but the third automation from the third industrial revolution, if we can call it, is in a different name, is more like simple or dumb automation, because machine just do things, not thinking, not judging, just doing very simple and say, okay, good or bad, or doing this or doing that. Very simple task. But for fourth industrial revolution, which we think that we can generate a smart factory, it is very different because it will be data-driven. Machine can think, process can think. Process has flexibility, not just automation. Okay. They can coordinate. They can have new party joining in easily based on the needs. They can quickly change the line. They can do scheduling under this kind of circumstances. So what will be the key technology to enable or to support smart manufacturing or smart factory? I think you probably know the answer. In Industry 4.0, basically, they said that German said that the underlying technology is something called cyber-physical system. Cyber-physical system. Physical system having this cyber capability, I will interpret it that way. So machine usually was machine do precision work, follow steps. But now machine has an IT, a brain, so that machine become more intelligent. Machine can connect to machine. They can coordinate and they can change. It doesn't have to be receiving the command and do it. Before you finish doing it, you cannot make any change. Now machine can always request, carrying dialogue, change their process, and change their process according to the condition at the time. I have quite a few examples on that, but anyway, so cyber physical system is the underlying technology that is making physical system cybernetic, having cybernetic capability, making machines having more IT capability, allowing machine utilize the power of digital system. Okay, so hearing this, you can probably also guess what I'm going to say next. That is, underneath cyber physical system, if we look at the more fundamental technology, it should be Internet of Things. In fact, this is what Germany defined. They define cyber physical system or Internet of Things are the fundamental technology for Industry 4.0. So building up this infrastructure in the manufacturing environment, allowing us to have smart factory doing smart manufacturing, and allowing us to enable this Industry 4.0 that is changing the brick and mortar manufacturing system into an IT system. IT system having being able to utilize all the IT functions that we are familiar with. So for information system department, although we are probably working more on enterprise system, but in the future, I think a lot of knowledge and functions that we learn from the enterprise system can also be transferred to the factory, allowing factory to be even more enhanced. So just to reiterate what I described earlier, from first industrial revolution, mass production, first industrial revolution, machine replacing human, and we do customization, just like machine is more powerful, so we can do it faster. Second industrial revolution, we do mass production, so the product types becomes very few, and the quantity becomes abundant. A lot of product of the same type. I think there was a joke that is when mass production just started and people question about mass production, they asked the founder of Ford Motor Company whether or not he can produce a vehicle, different types of vehicle. And Henry Ford famously said that Ford can produce cars with any color as long as they are black. So once they do mass production, they focus on mass production, but the variety will be very limited. They focus more on quantity rather than variety. And after the Wide Web started to be introduced and e-commerce started to be introduced around year 2000 or before year 2000, the model of mass customization came out. That is using mass production technology, cost, and time. Of course, with certain variation, we can produce so-called mass customized product. So it's not total customization, it's limited customization. So your car can change certain parts and not any color. There are certain colors that you can choose from. And or you can customize your windows, but only have certain specs. And there are also a lot of examples indicating supporting how mass customization can be done. So the needs gradually from quantity to variety. And looking into the future, we are not very certain how it's going to be, but we are pretty sure that customer demand will be more and more uncertain, and the variety that we need to produce to serve our customer will be higher and higher. That's the problem we are facing. So it further support that the core of Industry 4.0 should be customization rather than mass production. So in factory, if you look at more advanced factory, it's very, I mean, these are from Germany. It's very advanced. They have gradually they have all kind. They have introduced integrated all kind of IT technology, digital technology in the system, and along with that, then there are many issues that we need to address because we have machines talking to a machine. We need to have identification, right? We need to know which product belong to which customer and what kind of needs that this product demand. We need to be able to sensing and acquiring data all over the factory, right? In some factory, they said that they have more than 10,000 sensing points. I think in TSMC, they definitely has more than that in one factory. Because when we have that many sensing points, then it's not possible to use wired. So we need to have all kinds of wireless communication. Need to overcome all kinds of problems of wireless communication. When we have wireless communication, we have sensors, many sensors, and these sensors require energy. So low energy consumption for processing and transmitting data becomes an issue. And we need to do, in some cases, energy harvesting. We need to carefully manage our bandwidth, and we need to have human and machine work together. And we still have our strengths. We are more flexible. We are more, we move also with, mentally we are more flexible. Our movement is more flexible too. But we need to be able to communicate with machine and robots more effectively rather than always writing program to make changes. We hope that we can just teach the machine, teach the robots to do things in the easiest way. And also, we need to have a lot of intelligence, meaning machine can understand, recognize, make decisions, and so on. And different machines need to be able to be integrated together. So it also requires interoperability of machine, which is a big task. And a lot of data analytics and security and privacy issue. These are all the issues evolved during the Industry 4.0 development. But one thing we need to be aware is that despite during the same period, we have a lot of improvement on hardware. But hardware is not the core of the Industry 4.0. Software is the core of Industry 4.0. Hardware is just a carrier. It performs tasks. Software enables the hardware to have many functions. One example will be if we use camera to enhance the capability of the machine. So camera is just a hardware, but the software, the ability of the camera can be continuously improved. Right? Hardware, if they have certain precision, that's their precision. Right? It cannot improve it anymore. It's just very rigid. They can repeat many times. But in order to have more function, the system need to have this sensing capability, right? Being able to be more flexible. All these require software, and software can be enhanced continuously. Software software value can be shared by other machine. Rather than you are just improving on this machine, every machine need to improve. Once you have the software improve, this software can be used in other machines too. So it also implies a very different business model. But again, here, industry 3.0, the third industrial revolution, we change the machine with electronic and IT so that machine can do automation. Industry and machine was still the core, which is add a little bit of IT electronic. Machining stability and precision was still the core of the automation. But for Industry 4.0, machine is smaller, software is bigger. There are a lot of software solutions that we need to introduce to the hardware system, and there could be many different business models that we can generate. Okay, although we haven't reached that point, you see this example. In fact, I saw this similar case in China maybe 10 years ago already. They control their machine using a panel. A colleague of mine, whom I know for many years, they have, in China, they call it key laboratory on manufacturing, smart manufacturing. So they build this kind of function. They say, okay, I want to utilize this machine and doing certain tasks. They have an app. You click on the app, all the control came out, and you can just process this manufacturing with the app. Okay, so Industry 4.0 is more software focused rather than hardware focused. That we need to be aware. And if we look at the IT architecture in manufacturing, to the left, this is I think ISA 85. I don't remember. ISA, the architecture. That is, in the automation system, you have to have hierarchy, and in the hierarchy, you can only communicate layer by layer. If you are doing this layer, you can communicate on upper layer and lower layer. Okay, you don't communicate outside the hierarchy. Right? It's defined by ISA. I think it's 85 or 95. I don't remember. But anyway, it's for automation. They build out this architecture so that companies or manufacturers know that they are providing a solution at which layer, and they should be responsible for doing communication with the adjacent layer. Right? It's very similar to our network layer in IT system. But the problem is in the manufacturing environment, a lot of time the incident happen that require the system to respond, require them to communicate with different layers. Maybe I can give you an example. Let's just say if you have an AGV leaving the warehouse, bringing some material to some production line. So your AGV was given an instruction and bring the material to certain production line. So the AGV will leave the warehouse and go. But along the way, that production line has a machine breakdown. So definitely it will not require this material. But in the traditional system, what the AGV does is take the material from warehouse to a certain point. It will just continue to move without knowing anything, without communicating with anybody else until reaching the destination and the material being unloaded, and then the AGV will go back or receive a new command. It's very, very limited communication. So with Industry 4.0, what we really want to have is the flexibility. That is HEV living, and the machine has already broken down. So the machine said, okay, we have machine breakdown. We don't need to have the material. And the HEV will know. The HEV can request and say that, should I bring it back to the warehouse, or should I still go there, or should I bring the material to some other production line? And these other production line may be able to respond to the inquiry and say, oh, hey, I need a material in certain time. And maybe there are multiple production lines say the same thing. Then there should be a process to determine where this HEV should bring the material to. And such kind of information need to be shared to the relevant party and so on. So it can be done, but traditional IT does that. So to the right, you see the new connectivity structure. Like any device can communicate with any device, because they are having all the layer of the communication. Right? It's not they are working on one layer and going up and down. They have ability with all the layers, or cutting across certain layer, not necessarily all layers, but certain layers, multiple layers, so that they can communicate directly. This is the new network rather than this hierarchical one. And the hardware, traditionally, I said, they use their own protocol. Different companies use their different protocol. Unless they are pressured by their customer, they will stick to their protocol. And of course, there were some integration and there were some de facto or even so-called standard. But other than standard, or a lot of companies are still using their own protocol, which makes the integration very time-consuming. So in Industry 4.0, they are trying to come up with something called service-oriented system. They can do the service-oriented planning. That is, we'll share the hardware away from the software, making the functions, the capabilities provided by these hardware, making them into services. So they are all providing service. Different hardwares, if they can provide the same service, then we can utilize them. In the past, when we want to talk to them, then we need to deal with a protocol problem. But now, because we show them, we have a standard. Doesn't matter what kind of data format you have, but when we want to communicate with you, we have something more like API, so that we can communicate with different machines. And you, based on the service requirement, need to allow the system to know what kind of service you provide, what specification of the service you provide. So when we are coordinating the production, if we want to have a sensor, okay, we don't care which brand, as long as they can provide this sensing capability, getting us the data that we want, then we can just integrate them immediately. So these hardware will be shielded from the software system, and they will be represented by their service modules. And these service modules can be found in service library. It's just like service-oriented programming. And from the ERP system to manufacturing execution system to shop floor control, software, and software. So basically, they can use this kind of system, allowing our coordination and planning more effectively. Okay. Otherwise, we were planning at the corporate system or factory system, but when it comes to integrating, requiring certain functions, then we need to deal with integrating, reconfigure the hardware, and it takes a lot of time. But now we don't need to do that. So this is the kind of function that we need to have, because in the manufacturing system, we want flexibility. And earlier I mentioned about dialogue. This is also from Germany Industry 4.0, one of their presentation case. DFKI is German Research Center on Artificial Intelligence. So basically they came up with this framework. The AI is not necessary. I think right now we focus too much on deep learning, but AI is not just deep learning. They are talking about more on the semantic level. Right? Just like we are talking, we are not just sound, the medium of the transmission. We are talking about certain contents. We can reason with each other. We are talking in the semantic, at the semantic level. They want the machine to be able to talk at the semantic level. So here with service-oriented system, here's the case. A key finder is something that you attach to your key. So when you cannot find it, then you can maybe using app, it will find this and it will blink or sound so that you can find your key. And it has a few elements. There's a button, small chassis, there's a board, there's a top cover, and also there's a plate which you engrave certain characters. Of course, the inside could be, the board can be different. Just assume that there are different choices, maybe different color of cover and different engraving. Okay? Here, they use laser to write DFKI, maybe you can write ITS and so on. So they have such kind of customization. So what we may be able to do, again, this is their case study. What we may be able to do is, okay, if we said, even though the process seem to be identical, but there could be some subtle issues about carbon emission. So processes are the same, but the carbon emission from different machines could be different. So maybe this product requested for green production that require minimization of minimizing CO2 emission. So the system need to, there's an RFID tag. The process is a product. In fact, in the past, there's no conscious of the product. I mean, there are just lots of product being produced. In the end, we say, okay, this is your product, this is your product. There's no product in the beginning. For this service-oriented system, they change the role of the product and the system. Okay, the role of product and system is just like what I said earlier. In healthcare, individual patient try to fit into the mass production process of Medicare, right? And production is also the same. But now for Industry 4.0, they try to turn the central part of the relationship to product. So product right from the beginning, having an identity, knowing what the product needs, and the product even starting with nothing, going to the system, requesting materials and manufacturing process to realize the product. So right from the beginning, this is a customized, this is a personalized product, and going to system, requesting resources, rather than just go in, which machine has availability, go there being processed. In the end, we generate 1,000 products. Then we say, okay, this go to you, this go to you. But in this Industry 4.0 service-oriented CBS, what they can achieve is the central part of this relationship, machine, product, or manufacturing process and product relationship. The central part has been changed from machine to product. Just like Medicare, of course, I mean, for us, I think we will think that we are the the central part of the doctor and patient relationship, because we are the patient. We have problems that need to be solved, and we are paying for that. But in fact, traditionally, it's not the case. Doctor has much more dominating role in doctor-patient relationship. Patient can only follow whatever doctor allow the patient to do, and so on. And again, I have to say that, and I said it earlier, despite our feeling that maybe it seems that the healthcare is personalized, but it's not. It's more mass production. And gradually we want to change it to customer should be, or patient should be the center. And the service that the patient receives should be as personalized, as precise as possible. Okay, so in manufacturing, so the in the beginning, there's no elements there, but there's a product, a virtual product request coming, and the product demands on certain production process, and then the if we put on the carrier, an RFID tag will record its ID and all of its needs, and the routing plan will be downloaded to the RFID chip like this, and this product will start to or put on this carrier, and will start to request resources that meets the objective. Here is green production, and available machine will coordinate themselves among different requests and provide service. Once you finish the service, you go to the next station, you will carry dialogue with the machine. Dialogue is just a way to describe it, but basically the machine will check what the product needs. So the machine will say, okay, what kind of the processing you need? And the product will say, oh, I want to have low carbon emission process. Oh, the machine says, okay, I cannot do it. Maybe that machine can do it. So, and then that machine has availability, so the product will go there, and so on. So they in the German Industry 4.0, there are different showcases. Basically, what they show was product and machine can carry communication. So imagine that now we have a manufacturing system. Our process is not fixed, and we don't need to. So this thing comes, I just do the thing. So every time this product comes, the machine will ask what kind of service you need, and the product will respond. Or if the system suddenly crashed, when it's being recovered, then the product is there. Then machine can still ask, oh, what have you been completed? And then the product can continue its process, and so on. Just using dialogue to create flexibility. So we need to have semantic. We need to have not just communication, like protocol communication. We need to have semantic level, using the same language, using the same terminology, so that the system can communicate with each other and carrying dialogue, so that flexibility can be created. And in Germany, some years ago, also in India, and I have written a paper, maybe earlier I showed that it has been translated into Japanese, which I feel very interesting. So that we have this Industry 4.0 REMI. We describe this REMI architecture, or reference architecture model, Industry 4.0. This is very complex. So people are developing different parts. They need to know how they can position their work. Otherwise, it's very difficult to co-work on the development. So REMI provides more and more information, more and more context, so that we can utilize to contribute to the software development of Industry 4.0. And this is the shielding concept that I was talking about. There's something called administration shell for hardware. Right? These are hardware. So administration shell have their structure. So and we need to provide such kind of these administration shell serve like API, and it's defined. So you know when you request information, they'll put information following the format defined by REMI. And you can allow from lowest level sensor communicating with other sensor or device all the way to in the system. So there's layer after layer of administration shell based on what they need. Okay. So system has a big system administration shell allowing them to communicate. As I said, a single device has its administration shell allowing it to flexibly communicating with other administration shell. So these are methods that turns the proprietary hardware into a common software service so that we can utilize them more flexibly and we can integrate them with much less amount of time. And even for the entire system here, what we'll do is we basically, this is another example in Industry 4.0 or REMI. Basically, you can imagine that you can even have a digital twin. And this digital twin require different hardware information. And for certain hardware, their digital twin represent them to communicate with another hardware's digital twin. So this digital twin is basically taking all the software part, this data part of the hardware, allowing the system to be able to communicate with a different system. Okay, so this is again something that it is required at the software level. Conceptually, we said that we use service-oriented architecture. However, when we are implementing it, we need to have a standard. This standard was supported by REMI 4.0, and the API part is so-called asset administration shell. There are a lot of different detail provided. I did have a few students. Indeed did a little bit on REMI 4.0, and last semester or previous few semesters, I always had students working on REMI 4.0 and asset administration shell, trying to work gradually towards the software part or semantic part or service-oriented architecture part of the Industry 4.0. Okay. And in Industry 4.0 also, the cooperation or the collaboration of human and machine is a very important issue. We want to utilize the strengths of both systems. In the past, these two systems need to be separated because robot may injure human. So robot work in a cage or in a confined space. Human cannot enter that space. But what we want to do more is human and interact with the robot or machine directly, helping the robot to learn and working together. Like robot can take very heavy object and do very precise work. Human is more flexible. Right? Human know a lot more than robot. So if they can work within the same space, it will be even better. And there were cases I've also seen in some manufacturing system, like worker try to, for example, worker climb up to a very high place and robot can carry a very heavy object to the top and the worker just need to help to align a little bit, and it can be put down. In the past, if you want to have robot to take it up and put it down precisely, because it will have a lot of swing, and in order to reduce the swing, you may need to spend a lot of money doing that, and robot may injure a human. But now with the robot and human collaboration, or collaborative robot can work with robot together too, in the same space. Robot and human can work in the same space too. So there are many examples. The main requirement will still be robot cannot harm human. Okay, and there are cases receiving robotic, although they have unfortunately they are out of business. But it's still a very good company. They are still doing other things. This is the founder is the person who developed iRobot, the round robots sweeping your floor, and they are still doing other things. MIT professor. And Franca Amica is also a very interesting robot. Oh, I have it. So basically, the robot doesn't have eyes. Franca Amica's robot did not have eyes. I don't know whether or not now, but their sensing capability is amazing. Meaning, for example, the robot, you just put the robot to a certain, very close to your, say, your USB plug. They will just move very, very nicely. They cannot scratch the surface, but they can find the place and quickly insert the USB. Or I saw the demo where they use a knife, can punch into, say, fruits. And if you suddenly move your hand in between, once they touch your hand, it's still moving quite fast. It will stop abruptly. So very sensitive. Their torque, their response is very, very sensitive, so that it can ensure the safety of human. So they can also do something like grabbing something with enough strength. But when you are pulling this thing away from the robot hand, a human knows when to release, but robot may not have that kind of sensitivity to release it at the right time. So either you cannot take it, or robot drop it prematurely, and you may damage the product. So this kind of collaboration will also taught into Franca Amica. Very, very interesting robot. This robot doesn't have vision, or did not have vision. I'm not sure about now, but they do a lot of things that originally only human can do, because robot is too rigid. Their sense and response was not nice enough. So a lot of things that robot cannot do, but now gradually can be replaced by robot. AR system, I think you can understand. Right? We are looking at something, and suddenly all the information appear digitally on our eyeglasses. Right? So we suddenly know everything, but in fact it's not. It's based on camera and AI in the back, and AI's analysis result will show on our eyeglasses. This is also a very good human and machine integration. And or gradually we can have exoskeleton. Right? We don't have enough strength, but we are linked with a robot. Right? We move with robot. I think something which is already very useful, that we usually, if we do heavy work, it's very easy to injure our back. But if we have this exoskeleton, when we are lifting something or we are bending down, I think the exoskeleton should protect us. But the flexibility and of the human hands and other work can still be done, but robot can support us, connect with the human directly. And this is also a project that we are doing. Maybe later Indy can introduce it quickly. We do order picking in the warehouse. for e-commerce or any other warehouse, they will order, then there will be human going to a big warehouse and pick up items and prepare the item for shipment or for production. But in e-commerce, it became very difficult because you have so many SKU, stock keeping units in a very crowded place. People are interfering with each other. Traditional technology cannot improve the efficiency of order picking anymore. So Amazon came out with this. This method wasn't really created by Amazon, but Amazon utilized it in e-commerce warehouse so that the robot will take the shelf to order picker. So the order picker, human, the only thing that the human can do better than robot at this time is to pick. But traditionally, human need to walk, need to search. Those are non-productive. So rather than having many people walking, interfering, and search, picker just wait until robot come and screen on which layer, which compartment, pick certain item, how many pieces. The worker can do this. So the cooperation between robot and human is taking over humans' non-productive tasks, allowing human to focus on what human do best, that is picking, the flexibility, dexterity, or some of human hands. That is still very important. Indicate introduced that, but we are also working on with a very good logistic company on optimizing their system. This is also another kind of system. This kind of system will be more and more. Okay, it is also, we call it part to picker. In the past, it's picker to parts to pick. Now it's part to picker for picker to pick. And autonomous vehicle also provide a lot of opportunities. And for the entire smart manufacturing, there are still, as I said, issues that haven't been addressed. That is information sharing, particularly in supply chain. So blockchain can come in to help. And also for customization, a very important technologies, which is 3D printing, is getting more and more mature. With 3D printing, there's an issue that is a copyright issue, intellectual property issue. If I send a file for you to print the product for my customer, then you own the design file. You can print it, and I don't have control. So they also try to use blockchain technology to control the authorization of the production of the certain part, so that it can be connected to the product. So once you have a product and people challenge you whether or not you have infringed the copyright, but you can check on the blockchain and see that, okay, I have been authorized to use this machine to make this part for me. So that we can also ensure intellectual property for 3D printing business model. Okay, I think because of the time limit, I will just stop here. I think this is also a full cycle, although later, if we have time, I was going to share with you beyond just manufacturing, beyond just Internet of Things. I think in the future, biotechnology is also very important. And so-called data is the new mind. Data ownership, which we have incidentally, because of there was a question, I have also addressed that issue a little bit already. That is, data ownership is as important as data privacy, if not more. Data ownership, your data or the country's data, the city's data. So there need to be a balance. We want to have economic development, we need to utilize data, but we cannot infringe data privacy. But if we can protect privacy. If we protect too much, then there's no data economy. We cannot utilize these data. So on the one hand, we need to protect data privacy. On the other hand, we also need to provide data ownership so that we can support data economy. So this is also something that maybe in the future we can also discuss. But at this point, because I know that later we have exam, and I would also leave time for Indy to do a little bit of explanation on Kiva and later question and answer session. Thank you.
Okay, thank you very much, Prof. Chou, for the interesting lecture. Now we will enter the next session, which is a demo from Professor Chou's laboratory member. For the Prof. Chou's laboratory member, the time is yours.
Okay, Indy, I'll start sharing. So Indy, yeah.
Okay, wait. Mr. Indy.
Yeah. Oh, by the way, Indy should be graduating this semester, and hopefully that he will stay with us for some time. As a postdoc.
Congratulations.
Not yet.
Not yet.
Thank you.
Yeah, congratulations, Mas Indy.
Yes. Okay. Let me share. Okay. Screen one. Share. Okay. Can you see my slide? Yeah. Okay. So can you see my slide?
Yes.
Okay. Thank you very much. Today, good afternoon. Thank you for the opportunity. Today, I would like to continue what Professor already explained, especially about the robotic mobile fulfillment system. As Professor already explained, this robotic mobile fulfillment system, we can say that this is one kind of the collaboration between human and robot, and also this kind of implementation of a smart warehouse. Because in here that we use a mobile robot to move throughout the warehouse to bring movable shelves, so-called pod, which contain inventory back and forth between the storage area and workstation. Why do we need this system? Because as you know that during the pandemic, you know that the number of online purchase in online shop, for example, like in Amazon or the Alibaba, is increasing. So people move from the traditional market, move from the traditional shop to the online purchase. So because of the increase of number of online purchase, for sure that the number of order in the warehouse also increase. Yeah, for sure that we need to manage this one, because online or e-commerce has some characteristic. For example, it's also what Professor already explained. Nowadays that people tend to buy more variety items, but only like a small item. For example, in online purchase, that sometimes we buy only like a pencil, but also we buy maybe like tissue or maybe other things, but in the small amount, but the lot of variety. So as we can imagine in the warehouse, for sure, if we have like number of variety or large number of variety, so we need to have like a big warehouse. So as you can imagine, if like for my example, if I buy one item, then I need to buy other item, the picker. Usually it's human. If they want to take one item, then they need to walk through the aisle of the warehouse to take another item and then take other item. For example, if I buy 3 items, so they need to travel long walk. So this will increase the number of costs for sure that the long walk and also for the human effort. So because of this one, in like Amazon, this robotic mobile fulfillment system already implemented by the Amazon and now also Alibaba, if I'm not mistaken. So they're using robot in here that they bring the pot, the rack, with the item inside of the pot to the picker, the human picker. So they will coordinate by all of the central system to coordinate based on the order which one pot need to bring by the robot to the picker or picking station. So this one we can see in here that the decreasing operator moving distance improve throughput very much. And also the advantage is simplify human work with high level of human machine collaboration. Robotic mobile fulfillment system can not only be utilized in e-commerce but also in retailer and warehouse system. Okay, so Professor already explained that in robotic mobile fulfillment system, they have several kind of mobile robot. And also we have pod, we have charging station for sure. And this is the picking station to get the item from the rack. And then based on our order, and also there's replenish station for sure that the pot will be empty, then we need to fulfill again. And then for sure that the highway system. Okay, and this is the warehouse layout. As you can see, there is an area for the picking station and also the replenish station. And we have this one, the storage area. Instead, this one can be highway. And then this is the blue one is the pot or the rack. And this one maybe selected pot. For example, in here that robot will bring this selected pot to the picking station, or if they need to replenish, they will bring to the replenish station. And this is there is an aisle. Actually, the robot, if they don't bring the pot, they can also move throughout the behind of the pot. But if they bring the pot, for sure they need to bring it by the aisle. Okay. Actually, this is the simplify of the process flow of the robotic mobile fulfillment system. For sure, at the first, in the beginning, that we need to assign order to which pot that has that ordered items, and then to bring to which picking station. Then after we consider both of this process, then we choose which robot available that can bring that pot to the picking station, and then deliver to the picking station. And then after that, we return after the staff to pick the item. Then we need to consider how we bring to the storage area. In this one, sometimes we can bring to the original area or maybe other area that available. And then it's also same with the replenish pot. If there is a pot that's empty, so robot need to bring that pot to the replenish area, then fill again the item, then bring again to the storage area. So one of the conditions that we need to know when and what to replenish. So for sure in the picking station, sometimes it will happen queue of the robot to bring this one. It's also one of the problem that we need to solve. Actually in here, that we already has several problem that we can consider in here. For example, this is from the more in the strategic problem decision. For example, zoning, quantitative configuration, like the number of charging station, number of robot, number of pods, and etc. And then we need also consider about how do we put the SKU or the item in the pods, because different demand or different season, maybe we need to adjust how do we put the SKU to the pod. Also, how about the number of inventory level? Yeah, because this is also related to the number of demand and number of the process inside of the inventory. And then the replenishment policy. Yeah. For sure, this one is more in the operational problem. Besides this one, we also have like the order related tasks. For example, when the batch, when the order comes, do we need to solve one by one or first come first order, or we need to make it into batch order, or how do we sequence the order, and then how do we send or order to pod assignment? This is more on job assignment, and then order to pick station assignment. So for sure that this one we also can consider using data analysis, for example, association rule, clustering analysis, and ABC rule. Actually, in this one, we can also consider using the data analytics. For example, if we know about the pattern of the demand or how to demand in the future, we can also prepare for the setting of our SKU to pod or our SKU inventory level. And besides of this one, we need to also focus for the robot motion. For example, the traffic control. Yeah, because for sure, if we have a lot of number of robot or number of order, for sure, there can be a lot of traffic. Maybe happen like traffic jam, or maybe queuing. Queue is too long in the picking station or replenish station. Because if it's happened like traffic jam or other problem, it also can slow down your throughput. Throughput means it's how many number of order that you can solve in like a period of time. And this one, because we using robot, for sure that we need also consider about the energy consumption. Yeah, because we know that robot need energy, electricity. So if the robot has too many like turn left, turn right, or turn around, for sure it the number of energy will also increase. So maybe it's same like if you driving a car or riding a motorcycle. If you like accelerate and decelerate, for sure that you will have more energy that you use. It's same in this one. So for sure that we need to balance about the throughput and then energy consumption, because now we also concerned about the sustainability or energy conservation. So based on this condition, that we built a simulation platform. This is warehouse simulation platform. Why we using a simulation? Because a lot of real world system are too complicated to use, describe, and solve analytically. So we want to show based on the visualization result of statistic by using a simulation. In here that we want to enhance the throughput, conserve energy consumption of robot, and optimize the robotic mobile fulfillment system configuration. We use multi-agent simulation platform. Maybe some of you already know the NetLogo. NetLogo is multi-agent cross-platform modeling and simulation environment with high flexibility, then easily integrate with Python. Yeah, for sure, for the optimization or for some of the process inside of the NetLogo, we incorporate with the Python, for example, for the optimization platform. So, and also if we want to access like the number of order or the layout, then other, we can also using the Python and then incorporate with the simulation platform of the NetLogo. So we have this combination. Actually, one of lecturer in the information system, Mr. Ruli, also has some contribution in our initial process about this one and bit of process. Okay, so this is the simulation platform. Actually, this is in the early beginning, so they're still very small, but actually now we have a very big simulation. You know that number of the pod in here It's already more than 100, maybe it's around 1,000. And this one, the picker process, the picking station. And you can see the robot bring the pot to the picking station. And this one, the replenish. And you can see we can set all the initial setting in here. And some variable, decision variable, parameter in here. Actually, the throughput in here you cannot see because it's need like 3,000 something tick or process, and then they will show the chart in here. Okay, so actually in information system department, usually we combine between industrial. I know that you also learn about supply chain, inventory, then combined with the IT technology, for example, simulation and the coding. I think this kind bit of research will good for you. It will be very interesting. Also in Indonesia, we know that we have many online market, like for example, like Bukalapak, Tokopedia. Maybe in the future, they also consider to implement this kind of system in Indonesia. So this one will be good opportunity for the information student. Okay. Okay, as you can see, this one, the robot bring in one, but this one, there is some queue, but not too long. And they then bring to return to this one. And this is the replenishment process. Okay, yeah. Okay, I think that's all for, because we only have time. Actually, maybe later we can also discuss more about the, because we also have like more energy system and other interesting part like the advanced planning system, but because of time, maybe we can continue in the
maybe I just add a few words. NetLogo is a multi-agent simulation platform we built on top of NetLogo of this simulation system. So now we have this multi-agent simulation system that we can model any factory and perform simulation for them. What you are seeing right now is Carrefour, the retail store, their warehouse, and we are doing simulation. We model this and doing simulation for them because they are indeed mentioned about a lot of problems that we need to deal with. It's not just hardware there, things moving. In fact, we need to make sure that replenishment was done correctly, not correctly, most effectively, so that when we bring the part to all the picking station, there will be more items being picked, so that we can reduce energy consumption of mobile robots. And we can further, we need to determine for each SKU stock keeping units, how many items should we have in a warehouse, so that we can having a more compact warehouse. And maybe here we have 13 order picking station. Maybe for the order we have on hand, we only need to open 10 or 9, but can still meet the throughput requirement. All these need to be respond dynamically. So this system is very similar to what Indy has presented earlier, that for the parking case, releasing parking space is based on the demand. For water dispenser, for energy consumption, that is water processing, these water dispenser need to know how they are being used and change their water processing policy to reduce energy consumption. In this warehouse, although the hardware is already there, but because the order may change, like every day it can be changed, there could be seasonality. The warehouse should be able to respond dynamically to the order so that their process can be most effective. Okay, so we are working with a company which will export their system to Malaysia next year, 2023. They are building the building already, but they will take the hardware, the automatic, this IMFS system there, and we are providing this software solution for them so that they can continue to improve on their order picking warehouse performance. Okay.
Okay.
So
Thank you, Prof.
Sure. Thank you indeed. So, Raras.
Okay, thank you very much, Mr. Indi and Prof. Chou. Such an interesting research. Okay, now we will enter the Q&A session. If you have any questions, you can raise your hand and ask directly to Prof. Chou or write it down in the chat box. Meanwhile, I will give some explanation regarding the examination of Adjunct Professor program. Actually, to get the certificate of completion, you need to do two things. There are two requirements to obtain the certificate of completion. The first is you need to do the examination that will be held after this. And then the second, you need to submit the reports of your mini projects. The explanation regarding the mini projects and explanation already been added to the Google Drive. The Google Drive link is already written in the chat box. Intip in file Adjunct Prof 2002 DSI. But I will give a brief explanation regarding that. The first is I will explain regarding the mini project. Yeah, the topic of the mini project is IoT enhanced or enabled service. Okay. And the mini project reports need to include synopsis, the background of the topic, case description, proposed solution, and case analysis. And the reports can be presentation file with 10 up to 15 slides and submitted no later than 5th June at Western Indonesian time before midnight. And the mini projects will be done in self-organized groups, so feel free to create your own group, which consists of up to 5 students. And then the mini project should be submitted in the link below, okay, before 5th June at the midnight. Okay, this is about the mini project. And then we will also have an examination that will start after this. Okay. The examination will take about 30 minutes, open book. It will have 15 multiple choice questions and then 5 true false questions. The online exam will be held using Google Form and it will start after this session is closed. Okay, so this is the explanation regarding the examination and mini project. So you need to do these two requirements to obtain the certificate of completion on Adjunct Professor 2022 program. Okay. Now we will continue the Q&A session. Is there any question? Okay, if there's no question, may I ask a question, Prof. Chou?
Sure.
Okay, I'm very interested in your explanation, Prof. You said that in medical area, in which the patient go to see the doctor then examine the patient and prescribe the medicine. It is a mass production. Then what is the personalized product or service in that area, in that case?
Oh, okay. So my point is that on appearance, it seems to be customized, but basically, doctors know very little about the patient. So, for example, we go to a doctor and that's do you have a cold? Oh, you have a cold, or you have certain symptom. They prescribe medicine to you. Right, that's the beginning. Maybe that's a little bit customized. But in fact, doctor knows very little about you. And once the doctor prescribes medicine to you, and whether or not you are taking the medicine or conforming the treatment precisely, the doctor doesn't know. So next time you go, doctor say, oh yeah, it's not good. So two pills, or it's just try and error but basically it's still with a very discrete, like 1 pill, 2 pill, and I don't know you. I only know that the result is not good. So it's not personal. Personal should be, we go to the doctor. Doctor has a lot of information about us, right? Sensor information, exercise information, diet information, and maybe the doctor has prescribed medicine to us. People are still very different. So I wouldn't say that doctor can capture 100% of our unique parts. But then after, say, 1 month, we go back to the doctor, and doctor will say, oh, have the condition improved? Or maybe doctor will perform certain tests. But what doctor did not know is doctor will, based on the test result, to assess whether or not the treatment was effective. But the treatment being not effective may not be due to the diagnosis or the prescription. It may be because of you are not conforming to the treatment. Right? You did not take medicine. You did not take all of the medicine. You did not take the medicine on time, and so on. Doctors may not have such kind of information. So doctor's judgment is just based on a very simple part, that is, your symptom is still there, so I should increase the dosage. But I think earlier I gave an example on the smart pill box. That is, when you go to doctor prescribe medicine and you put the daily or these drugs in a pill box. So every time you open it, it will be recorded. The timing will be recorded, assuming that you are taking medicine at those times. So those information can be provided. If that is the only thing matter, then that information can be provided to the doctor. So when doctor, before you have outpatient visit, and or go to the hospital to visit the doctor, and doctor's examination result and your conformance on treatment can be combined to see whether or not the treatment was effective. Right? So meaning that doctor need to know more about individual before doctor can come up with more precise, more personalized service. If doctor only based on your visit and communication with you and the checkout at that time, assuming that the rest of them are the same for everybody else, I think that's mass production. Like me, in the beginning, I have a chronic disease, and in the beginning, I just feel that I was younger then. I just did not take medicine seriously. So if it wasn't effective, it's because I simply did not take medicine. But in recent years, I started to take medicine very seriously, like every day. I still don't miss it. So every time I go to the doctor, I recheck. Every time it was okay. So that is what I meant by even myself have such kind of difference. If both sides, the doctor feel that is effective or not effective, these two situations should influence tremendously. Like sometimes I miss the entire week until, oh, okay, maybe I should start to take some medicine. Versus right now, every day, morning and evening, I take medicine, right? Every day. So again, my emphasis is if the doctor can have more information about the treatment will be more personalized. If the doctor doesn't have enough information, and in reality, we say, oh, of course, doctor can have all kinds of checkout on me. It's very costly, very time consuming. We just don't have that kind of resources. But I guess if we can have different kind of sensors to users, maybe users, if you have diabetes, maybe user can have a camera taking photo of the meal, and now I think a lot of stores, they have their QR code you can scan. They tell you how much calorie, what ingredients that you have, and so on. If you can collect all such kind of information. In fact, I did a work with a doctor maybe close to 20 years ago on this. It was very difficult, but now it's very easy, right? You just take a photo. You don't even need to have the QR code. The photo can recognize what kind of vegetable you have, what kind of meat you have, although not very accurate, but they can even judge. For example, I take a product. I use Google, what's the function? But anyway, I take a photo of it. Google give me the name of the product, like the link and so on. So basically, more and more information are provided online, and users can use some devices connecting this information, your physical activity information, and make them digital and provide this information to doctors. And on the doctor side, doctor can have information, system to analyze such kind of information, combining with his or her treatment. Then the doctor can make more precise diagnosis and changing treatment accordingly.
Okay, thank you very much, Professor. Your explanation is very clear. Yeah. Okay. Okay, is there any question from the audience? Okay. Unfortunately, the time is running out and we must end our discussion today, even though it's such a very interesting and insightful discussion. But yeah, we have a limited time, and after this, the participant needs to do a final examination. Okay.
Right.
So before we end it, I want to make a simple summary about today's. Okay. Maybe Mr. Mujahideen, as the head of the Information System Department, want to greet Prof. Chou.
Okay.
Thank you.
Good afternoon, Prof. Chou.
Good afternoon.
Prof. Chou has guest lecture as Adjunct Professor for 4 sessions to our department. I hope that at another time, Prof. Chou can meet again with me. And then, for information, NTUST give our alumni the opportunity to study doctoral program at NTUST. Her name is Bu Ima. Bu Ima applied to doctoral program at NTUST. Thank you, Prof. Chou.
No problem. Very happy to have opportunity to have exchange with your department. I'm very happy to see you and Irma and two Raras.
Yeah.
Thank you very much, Professor. Yeah.
Thank you very much, Prof. Chou.
You're welcome. You are most welcome.
Okay. Now I want to make a simple summary about today's topic. Industry 4.0 is highly related with cyber physical system, Internet of Things, Internet of Service. Therefore, we call it as Industrial Internet. Industry 4.0 is about the growth of personalized products and services. And in his lecture, Prof. Chou already gave us a very elaborate explanation regarding the example of personalized products and services from many areas, and also the concept to achieve it. I would like to say thank you once again to our honored speaker. Thank you very much, Prof. Chou, for sharing your experience and expertise regarding this topic. And on behalf of the Programs Committee, I would like to present the Certificate of Appreciation to Prof. Chou as the speaker of Adjunct Professor Program 2022. Okay, thank you very much, Prof. Chou, because you for your willingness to become our keynote speaker in this program.
Thank you very much. I'm very happy to have the opportunity and continue to hope that we can in the near future can meet each other and continue our exchange, not just on teaching, also on research.
Okay.
Thank you.
Okay. And before we end this event, let's have a photo session. For all of the participants, please turn on your camera. Okay, I will take the picture for the first slide in 1, 2, 3. For the second slide, 1, 2, 3. And for the last slide, 1, 2, 3. Okay, thank you very much. Okay, this session is the closing of Adjunct Professor Program 2022 about Internet of Things enabled service. On behalf of the programs committee, I apologize if there are any mistakes in conducting this program. To obtain the certificate of completion, I want to remind you that you need to do the exam and for 30 minutes until 20 before 6 p.m. in Western Indonesian time. And also you need to submit your mini project no later than 5th June according to the mini project description in the Google Drive. That's all. Thank you very much and see you in the next Adjunct Professor program next year.
Thank you very much, Professor Chou. Yeah, Mas Indi, thank you.
Terima kasih, Bu Irma.
Okay, see you next time, sir. Thank you very much. Yeah, Mas Indi, thank you, Mas.
See you.
Yeah, sama-sama Bu.
Congratulations, Mas Indi.
Thank you.
Thank you.